To today's seminar, and it's my great pleasure to introduce Luca Fossati, whom normally I don't have to introduce because you all know him. However, still, let's introduce him. So Luca studied in Italy, but has went on ESO studentship to Chile before going to Vienna for his PhD, where he graduated in 2009 under the supervision of analyse. So as you can see, a very long time to Austria already. Then he went as a research assistant to the European University in the UK. And you're still a research visiting fellow there. And in 2012, 2014, he went to the University of Bonn as a postdoc at the ÖAW-Institut for Astronomy. In 2014 to 2015, he became Alexander von Humboldt Fellow at the same institute. And since 2015, he is the group leader here at the Institute for Research and doing all this. And today he's talking about POLLUX, which we hope to bring to the Habitable Worlds Observatory.
Correct.
Thank you.
Thank you very much. So, I'm going to present you first the telescope, or better a mission, or better an observatory. It's more than a telescope, it's an observatory. Then an instrument, and then what's the science, the exoplanet science that we want to do with this instrument. The instrument is called POLLUX. And what is POLLUX? POLLUX is a candidate. It's not yet an official instrument. It's a candidate European contribution to the Habitable Worlds Observatory, or ÖAW. And it is a high-resolution spectropolarimeter that goes from the far-ultraviolet to the near-infrared in almost continuous and simultaneous way. Okay, so it covers the entire UV and optical and near-infrared band in almost one shot. So you see here from where ÖAW comes from. So ÖAW is a flagship mission, is a NASA flagship mission that has come out of the latest decadal survey. And these are the different missions that have come out from the astronomy decadal surveys over the years. The first one was Hubble, then came Chandra, then Spitzer, then after a very long time came Webb. And Roman is going to come very soon, I believe next year, maybe 2 years. And then ÖAW should be the next one. You see 2030 something, and originally it was 2040 something, but NASA is rushing, and it should then, because that 30 something should hopefully be 39-ish. Okay? And this is one of the possible configurations of the telescope. I'm going to show you this in a minute. So what is ÖAW supposed to do? Here you see different science questions that ÖAW is going to touch with its different instruments, but those that are most relevant to us, that are relevant to planets, are how does our solar system fit in among the other planetary systems? Are there habitable icy worlds in the outer solar system, and is there life on exoplanets? So ÖAW is going to touch both solar system science and exoplanet science. This is the roadmap towards making ÖAW real. So I'm trying to guide you through this. So this EAC 1, 2, and 3, these are concept studies for the telescope. Okay, there are 3 concept studies. I'm going to show you those in a second. They are currently being studied. AC1 is finished. NASA is working on AC2 and AC3. They are meant to learn something about how to build the telescope in such a way that the instruments, and in particular the coronagraph, which is the key instrument of the telescope, in particular the coronagraph, is going to work as it should. And out of those, they are gonna figure out which is the best kind of design for the telescope, and they are gonna then study further. They're gonna fix the basic design and then study further the optics of the telescope to come up with AC4 and 5. Out of AC4 and 5 should then come out the final design of the telescope, which should then become the baseline. And out of this then comes together the science requirements. Now, there is an important thing here, TRL5 milestones. That's very important together with the maturity concept level 5, in 2029. This is very important because HWO we want for, and all the instruments that are gonna go on board of that, we want the entire technology to be a TRL5 by 2029, which is a rush. Okay, essentially, we're going to fly this thing in 2039 with technology of 2029. Okay, so at 2029, technology stops. Technology development. Right now, we're here. Okay, so we have to go through all of this before getting to a mission that stands on feet. This is essentially the same thing that I showed you before, but now in a timeline. We are currently, well, we are here. This community science and instrument team and HW advisory board. This call is already open, but we can't apply to it because it's only for US based people. There will be the HW conference in July. Which apparently has already something like 700 participants registered. It's going to be an insane conference. So the telescope should be then selected around the middle of this year, and then start the development of the next two telescope designs by the end of the year. Instrument study starts here. And you see all the different things that are going to come. There is something missing here, which is completely unknown. It's the most important thing for us is when does Europe start, if at all? Okay. It's missing. We are organizing POLLUX in such a way to be ready for a POLLUX proposal to be submitted as early as the end of 26. Okay, so we want to be ready. We want to have all the work done so that we can submit a proposal to ESA in case that comes at the end of 26. Then if it is in 27 or in 28, better. I mean, we have some more time, but we want to be ready by the end of 26. Because we don't think that ESA is going to do anything before that. Okay. So these are the three telescopes that are currently being studied, and you can see there are a couple of interesting things. You see that there are two, this one and this one, so 1 and 2, which are off-axis. So the off-axis means that the secondary telescope, the secondary mirror, is not aligned with the primary. You see, it lies underneath. So light goes into the primary, then bounces to the secondary, which is down, and then it goes behind the telescope, okay, behind the primary mirror. That's off-axis. And these are the first two. And then there is one case study of an on-axis telescope. Why there are two off-axis? Because the coronagraph likes off-axis optics, okay, and does not like on-axis optics, which is exactly the opposite of what the polarimeter likes. Okay, because every single off-axis reflection polarizes light. So all the light that comes to your eyes is polarized. Okay, because it comes from some reflection, except from the light that comes directly from the sun. Okay. It's always practically, with our eyes, it's always an off-axis reflection. That's why all the light that comes to our eyes is polarized. this would be the ideal telescope for us, but we think it's not going to happen. Okay, we think it's going to be an off-axis telescope, which for polarimetry is not ideal. It just means that we'll have to do a hell lot of work on calibrating the light that comes in. The other interesting thing that to notice, well, first of all, is the size. You see the telescope, they are, all of them are larger than 6 meters. Just for a comparison, Hubble is 3.4 meters. The other thing is that there is this configuration in where the entire telescope fits into the fairing, into the rocket, without needing to fold the mirror like James Webb. Okay, while the other two cases you have to fold the mirror in a way or another. Okay. The other interesting thing is that all of these configurations they are significantly easier to unfold and then build essentially in space compared to James Webb. Okay. So this is a lot easier. You see that there is no super thin, tiny, giant shade that has to come up at the bottom, has to open and unfold in a certain way, otherwise the entire thing goes bazinga. Okay. So this is technologically on this side is significantly easier than James Webb. All right, these are the instruments that are supposed to go on HWO. So here is the telescope. There's going to be a coronagraph that's going to work from the near UV to the near infrared. This is supposed to be capable of directly image an Earth-sized planet orbiting a sun-like star, nearby sun-like star. Okay, that's the goal, and to be able of do low-resolution spectroscopy on these planets.
Just out of curiosity, when you say nearby, are we talking 10, 50, 100 parsec?
It depends how well they're gonna be able to make the coronagraph, but the rough number is about 15, 20 parsecs.
That's a bit too far for our disks, but yeah, thank you.
There is going to be then a high-resolution imager. This should have a giant field of view, and it's going to cover practically the entire bandpass that the telescope can cover. Then there is going to be a multi-object spectrograph that's going from the UV to the optical, and this is a very complicated instrument because it should be capable of doing multi-object spectroscopy. Should be able to do imaging as well and imaging spectroscopy at the same time. So essentially, you take an image and all the side sources that are on the image getting a spectrum of, okay, in one shot. So it's a very complicated instrument that probably will require to be somewhat, and you see the resolution is low, it's not super high. We require to be somewhat simplified until it gets to maturity. And then there is a slot for a fourth instrument that's yet to be defined, and that's where we want to sit. That's where POLLUX wants to enter in the game. Okay. Politically, we don't know how this is going to work. Probably the US would like to have, so certainly the coronagraph will be American. There will be American flag on that. There's lots of European knowledge into it because they don't have all the knowledge that they need to build this. They need Europe for that. This will most certainly be an American instrument. This is the instrument that they would be willing to outsource somewhere else. But there'll still be the fourth instrument, fourth slot to be allocated. Where the instruments go, I can try to show you. So you see here, this red ring this is the instrument bay, okay, where all the instruments are gonna sit. And HWO is going to be built in such a way that all 4 instruments are independent, and someone or a robot can go there, take the instrument, take it out of HWO, either bring it back or throw it away and substitute it with something else, or repair it and then take it back in. Okay, so the entire mission, the entire observatory is the concept is that it has to be serviceable, like
But it will be L2 or
L2. Okay. After James Webb, they said every single major observatory we built has to be serviceable, regardless of where it is. Okay, because with James Webb it was too risky. You know, if something goes wrong, and you know that you've built this $10 billion thing and you throw it away.
Oh, that's the animals approach.
Okay. All right, let's come to POLLUX. Sorry, obviously the fact that it has to be serviceable puts quite a few constraints on the instruments. Okay, on the on how you have to design them. Okay. All right, so let's come to POLLUX, which is, as I said, high resolution shared spectropolarimeter. It has high spectral resolution, spectropolarimetry. It has a very broad wavelength coverage, nearly simultaneous wavelength coverage, and high wavelength stability. The wavelength stability comes on its own because it's a polarimeter. You can't build a spectropolarimeter without having high wavelength stability, simply because otherwise you get lots of instrumental signal. It has 4 arms, so what I'm saying is that this is not one high-resolution shared spectropolarimeter, but are 4 high-resolution shared spectropolarimeters, okay, all in one. There is a far-UV spectrograph, where you see here the wavelength range, so this is in nanometers, with a high spectral resolution, 120,000. Then there is a MUV, NUV, and the NIRO arms. This stands for mid-UV, near-UV, and near-infrared and optical. Okay? These 2 are currently, by design, simultaneous. There is a dichroic that splits the light in 2 and sends the light simultaneously into the MUV and NUV arms, and you get the entire thing covered in one shot. And we're currently seeing whether we can do all 3 of them simultaneously, and you'll see in a few minutes why. We think that's important. We have 3 main science themes within POLLUX, and the 3 follow the 3 main science themes of HWO. We have stellar and galactic science. Anna Ines is the lead. But we will probably substitute her with someone else in the near future. Then there is me. I have been leading the Exoplanet science case since the beginning, 2017, but I'm gonna give my position away, hopefully soon. And then there is extragalactic science, which is now led by Frederick, who is a lot more active compared to the one that we had before. So now let's come to exoplanet science. Exoplanet science, the science case contains also the solar system science case, of which I have to admit I know very little so far. It's in the building, in the development right now. I hope to know, well, I will certainly know a lot more by the end of March, because we're submitting it to NASA. I'm submitting the solar system science case to NASA at the end of March. So hopefully I will know a lot more about it. But in general, the things that the exoplanet science case is covering are atmospheric characterization, star-planet interactions, interiors, surface, and escape. So now let's focus on the exoplanet side of things. You see here a plot that shows the amount of flux that each exoplanet that we know of receives as a function of the radius of the planet in Earth radii. This is in units of what the Earth receives. So Earth lies at 1, 1 here. Here is Jupiter. And you see structures in this plot. There are in particular two structures, which are these, are the subjovian desert, which is this lack of planets here, and here there is the radius gap. If you do a histogram of the radius distribution, you see a bimodality. These are all structures, and there are many others in this plot that I'm not going to highlight. All these structures are done by mainly by two things: planet evolution and planet formation. Okay, these are the two things that are responsible for this structure and practically how planets look like. Okay, how do we study evolution and formation? So there is one thing that we like, particularly Helmut and I like a lot, which is that affects planet evolution, which is atmospheric escape, and planet formation. If you want to know about planet formation, you need to know how planets are made of. Okay, so the composition of planets. So the two things that we want to look at are how planets lose their atmospheres, if at all, and to better understand how the atmospheres evolve. And the second is of what these atmospheres are made of. Okay. So let's start with atmospheric escape. I'm showing you here 3 plots. These are examples. You see Lyman alpha. These are profiles before and after transit, and these are profiles in transit. So you see Lyman alpha absorption from a planet. Here you see carbon-2 absorption. This is in far-ultraviolet. This is also in the far-ultraviolet. This is carbon-2 absorption from a planet with a heavy mean molecular weight. It's not as, doesn't look as much like the Earth, giant and the Earth, somewhat in between. And you see here the study in the near ultraviolet of metals in the atmosphere of a hot Jupiter. And also this is to study the uppermost layers and constrain mass loss. And out of these observations that you can do only from space, because they're all UV observations, you study the characteristics of the uppermost layers of an atmosphere, so the temperature, the density, the velocity of the atmosphere. You can constrain the composition. Like here, we know that there is carbon in the atmosphere, and we know from that how much carbon there is compared to hydrogen. We can constrain mass loss rates. We can constrain stellar wind properties, particularly from observations like this one. We can detect secondary atmospheres with observations like this one, and we can indicate whether an atmosphere has aerosols and what is its plausible composition from observations like this. Another way for studying upper atmospheres and therefore atmospheric escape is looking at a helium triplet, the helium-1 triplet, which lies in the near infrared. This is a metastable line, or better, metastable triplet. What metastable means is that there is a certain level of helium, neutral helium, that gets populated, and that level is stable for a certain amount of time. And this time is not very, very short. It's of the order of half an hour to 45 minutes. And that's why it can populate. And that's why you can see lines out of that, coming out of that triplet. These are observations. Here you see observations. Here you see other observations and modeling that is done with it to constrain different things about the star, the stellar wind, the helium abundance. So you can constrain all these things out of these kind of observations, and they are very much complementary to what Lyman alpha can do. Now, why do we want to go to space to observe something that we have been observing so far, mostly from the ground, which is the helium-1 triplet? There are 2 reasons. The first one is that there is telluric contamination where you observe from the ground. You have lines that come from the Earth atmosphere that are in between that build up in your spectrum, and they may fall onto where the helium lines are, and then you have a problem because you have to remove the telluric lines. And then there is another thing. These helium-1 lines, they form in the star as well. Okay, and they are very much reactive to whatever the star does. So if the star sneezes, because at that moment it has, I want to be more active, those lines are going to see it immediately, and maybe you can think that whatever that you see happening on that line is due to the planet, but in reality is due to the star. However, there are other lines that can tell you, oh, that change in the spectral line is the star and it's not the planet. Okay, there are other features. There is H-alpha, sodium, calcium, but they are not great. The best lines are in the UV. So if you can cover at the same time helium-1 and the UV, you get a much better handle of what the star is, which is the stellar contribution in the variability of the helium-1. Now, there is also another kind of atmospheric characterization that is currently being doing very much, and it is using ground-based high-resolution spectroscopy, particularly in the near-infrared regime. And how does that work? You take the spectrum of the star in transit and out of transit. You take it out. You take out the spectrum of the star, and you're left with the spectrum of the planet. The problem is that the spectrum of the planet is embedded into the noise, and the noise is much, much stronger than the spectrum of the planet itself. So what you do is that you use models like these ones of, you see, water, HCN, and H3, C2H2, CO, of different molecules. You put them on top of your observation of your noise plus planetary spectrum, and you do cross-correlation. Because in that noise, there is a pattern. And that pattern is the one of the planet, is the one of the molecules of the planet. And you want your cross-correlation to recognize that pattern and extract it. What you get out of this are maps like this one, because cross-correlation is done in velocity space, and are maps like this one, where you get, hopefully, a detection when the peak of your cross-correlation function is at the velocity that you are expecting. Okay, at the velocity of the star, because everything is moving together, star and planet, and at the velocity of the planet, because the planetary lines, they move as the planet transits in front of the star. Yeah, can you follow me? Good. This is great because it works also for non-transiting planets, because you can do this in emission as well. Okay? Because the planetary lines move time, because the planet moves around the planet moves around the star. So because of Doppler shift, the planetary lines move, but the stellar lines stay fixed. And that's how you can distinguish between planetary lines and stellar lines. Okay? And that's why this works also for non-transiting planets. Okay? Good. And what you do, you can constrain the properties of the lower atmosphere and the atmospheric composition. Why do we, you can do this also in the UV. This is something that hasn't been done so far because we haven't had the capabilities, the instrumental capabilities of doing this so far. But there are obvious molecules that are very, very interesting to study in the UV. And you see here O2 and O3, ozone. There is a giant band of ozone in the near UV, and that's the reason for which we are on this planet. Okay, because it is this giant band of ozone that is absorbing the UV light that comes from the sun. So if we can do these kind of observations also in the UV, we gain access to ozone as well. One of the problems of doing this in the UV is that we need to know molecules and molecular lines, where they are and their strength very well, which is something that we don't have at the moment in the UV, but we're currently working on this. So we have Elias L, who is a PhD student at the ÖAW, who I'm co-supervising, and who is working on this and doing the observational part of the theory side that is done by ExoMol in UCL in the UK. And there are other very important molecules in the optical and near-infrared band. Why do we want to go to space to do this? So it's going to be absolutely revolutionary going to space to do this. And there are two reasons for that. The first one is that we are not going to have telluric lines, so lines from the Earth atmosphere. And the second one is that we don't lose the continuum. When we do observations on the ground, we lose the continuum. And the continuum is going to tell us a lot of things about aerosols, for example. So look at this. This is the Earth telluric spectrum. Okay, this is mostly, you see, this is water in the Earth atmosphere that is absorbing. So imagine having to detect water on a planet, okay, with the water lines in between from our atmosphere. Okay, being absolutely sure that the lines that you have detected of water are those of the planet and not those of the atmosphere after you have removed the contamination from the Earth atmosphere, you know, it's tricky. It's not the easiest thing. Yeah. If we go to space, and POLLUX is the only instrument with this capability because of the high resolution. This needs high spectral resolution and wavelength stability, which are the two things that POLLUX is going to have. This is the very first thing. Getting rid of the telluric contamination is absolutely important. If you ask anybody who is doing this kind of work, telluric contamination is the most problematic thing of these kind of observations. Second thing is, if we retain the continuum, we are going to get information about, you see all these changing slopes. That's most of them, it's either an effect of abundances or an effect of aerosols, which we lose completely when we do this kind of observations from the ground, because we have to normalize the spectra to the continuum. We lose the continuum information. By going to space, we retain the continuum information. So we have the continuum and the lines at high resolution. We have both of them at the same time. So this is a picture that I'd like to have as soon as POLLUX is up there. Being capable of doing all in one shot, with one observation, we observe one transit of a planet, and we get all at the same time, Lyman alpha, carbon and oxygen, plus a lot of other things, magnesium and iron in the near UV. We get molecules from the near UV in the optical and near infrared. We get H alpha and a bunch of other lines in the optical. We get helium-1 and aerosols. We do all of this, we can constrain all of this at the same time with one observation. Now, consider that each of the plots that you see here, except those ones which are modestly, every time you do one of these kind of observations, you publish a paper. Okay? One item here is a paper. Now imagine having the possibility of doing all of them at the same time. These are data sets that can last for decades, that people can work on for decades. Okay. So one of the, I'd say, super duper goals, I think, of what we are doing in exoplanet science, particularly on the modeling side, is having the capability of modeling an entire atmosphere from the bottom to the top, which is something that we haven't been capable of doing. One of the reasons that we lack observational constraints that cover the entire atmosphere in one shot. But now with this, we have the possibility. So we constrain the lower atmosphere using James Webb, and we have continuum information from it. Now, if we go to higher resolution and we do things from the ground, that's the part of the atmosphere that we cover. Okay, but we lose the continuum, therefore we have no aerosols information. And if we go in the UV, we have all of this information from many lines, also from the ground, from the helium-1, but we cover this part of the atmosphere. And if we want to do now all of this at the same time, we would have to observe with HST, James Webb, and from the ground at the same time. We've given it a try. It's impossible. Okay, it's not even if they would all be happy and giving you the time to do this, it's practically impossible. You can't schedule also because of problems that the HST has. Also, you would have to observe with HST with multiple instruments at the same time, which is not possible. But technically, it's impossible to do. With POLLUX, we can do all of this in Washington. Okay, and you can find your favorite adjective for describing how this would be. Okay, let me go through the other science cases. So we have star-planet interaction, and this is to study the magnetic connection between stars and planets. There are a few cases that we know are very interesting. One of those is 55.3, that's described here. You have the planet that's orbiting inside the Alfvén radius of the star, and from time to time it goes out of the Alfvén radius, from time to time it goes back in, or out and in. So you have continuously magnetic reconnection and deconnection, I don't know how to call that, between planet and star continuously as the planet orbits. And we see very strange things for this planet, for example. We see that the phase curve, the amplitude of the phase curve, so the amount of light that the planet reflects as it goes around the star, changes continuously from month to month. Okay, so from time to time, the planet is black, and from time to time is very, very bright. And also the secondary eclipse. So when the planet goes behind the star, you should have a tiny dip of light because you don't have anymore the light that is reflected from the planet. Well, the secondary eclipse, from month to month, sometimes it's there, sometimes it's not. And the depth of the eclipse changes continuously with time. And there is no time, there is no periodicity with this. It's fully random. And probably it has something to do with the fact that the planet goes inside and outside the Alfvén radius of the star. That's the only thing that we can think of. So being capable of doing at the same time, starting mapping the magnetic field of the star, thanks to the spectropolarimetry, and doing the observations of the reflected light from the planet at the same time, that will certainly help trying to understand how the star-planet interaction occurs and happens. Another thing is surface composition. So there are planets that are very close to their host star. The atmosphere is completely gone. They are subject to intense sputtering from the stellar wind. So there are atoms that come out from the surface of the planet, and they form a tiny exosphere around the planet. And this exosphere might be observable. And that exosphere, what is in that exosphere reflects the composition of the surface. Okay, so from being capable of detecting the exosphere of the planet, we can reconstruct what is the composition of the surface of the planet. And this is what we hope to be able to do. We have done this theoretically, and we hope to be able to do it observationally as well. Okay, we tested this with HST, it can't be done. We need something bigger like ÖAW, and we need high resolution for POLLUX. And then the last science case is white dwarfs. And why I'm talking to you about white dwarfs when I'm talking about exoplanets, and that's because in theory, white dwarfs, they're made, the atmospheres of white dwarfs, they're made just by hydrogen and helium and nothing else. But there are some white dwarfs that show metal lines, and you see here an extreme case, okay? From where do these metals come from? There shouldn't be any metal on the atmosphere of white dwarfs, simply because when a metal falls or is in the atmosphere of a white dwarf, the gravity is so strong that that atom just sinks on the core, okay? And that's why there should never be metals in the atmospheres of white dwarfs. But we see that. And that was actually, not this one specifically, but this kind of observation has been the first time that an exoplanet has been detected more than a century ago. Okay, when the first spectrum of a metallic white dwarf, that's what it's called, has been taken. Because what they have seen were rocks falling onto white dwarf. And what these rocks are probably remnants of a planetary system. So from doing these kind of observations, with these kind of measurements, that for which you require a UV high resolution spectrograph, you can figure out of what these rocks that were once a planetary system are made of and now falling onto the white dwarf. And I'm going to leave you with a summary of the different cases.
And so now we have the time for questions. Start with the union person.
So thank you very much. This is a really, really cool project. And you certainly sounded well to me, for what it's worth. I wish I had a few $1 billion. But one question that I had was, so you mentioned earlier when you talked about this cross-correlation method for picking up planetary atmospheres. Now, I did a bit with this, but it's been many years. You mentioned that you can also do this for planets that do not transit. How well does that work if you have, say, a planet that is embedded in a protoplanetary disk? Could you comment on that? Because I can imagine it makes everything a lot harder because there is a lot of reflected scattered light going on.
Oh yes, it's going to be a lot more complicated. I don't know if it would be feasible at all or not.
And also the orbital periods very large.
So
such a planet.
I know it's been done for like very wide orbit planets.
Okay.
Right, these wind speed in directly imaged planets paper. And since you have stupidly high resolution, maybe you can get ahead with this.
Yeah, if we know where the planet is and the entrance is small enough that the star remains out, it would have to be really far away from the star. We haven't looked at the entrance yet into the instrument. That's one of the things we will have to do in a year or two. That really depends how the entrance is designed, I think.
Thank you. That is like I have no idea of what the constraints are that you are dealing with. So,
But it's a very good thing to start thinking about.
Actually, the same thing with life. So we're also trying to establish it's an exoplanet instrument, but maybe one can do also something for the disk case, and we want to figure this out.
Oh, we have a giant disk package into the science, but it's in the star. It's in the stellar science case. Yeah. There is a giant disk science, which I don't know much about.
Okay, I have 3 questions. A short one is for the cross correlation. The atmospheres also have velocity fields. Does that confuse the cross correlation somehow? Because I mean, it lives from different velocities, right?
Yes. So far, the accuracy that we have on the cross correlation measurements that we get is not high enough to be able to split that.
Okay. Right. So
Maybe
yeah, that would be great. 5500 which one magnetic field strength has been guessed?
The star?
Or no planet?
Well, we have no clue.
Okay, good. Oh, it's back. Then for the white dwarf, I mean, this is fantastic. And at some point we tried with Oliver Herbert actually to use the elemental balances from white dwarfs to have a go on exoplanetary elemental balances. The problem is they're only looking at a certain wavelength range, so you're missing a whole bunch of elements like oxygen, for example. Have you an idea how people from the white dwarf community are dealing with that? Because the great thing is that if you would get the entire set of elemental balances from the white dwarfs.
So the problem is that they haven't been able to measure oxygen so far because they have observed with HST, and HST has HST is in near Earth orbit, and Earth has geocoronal emission that is at Lyman alpha and the oxygen, and that covers the oxygen lines that you would use on a white dwarf. But if we go by going to Earth, then we have the oxygen lines and we'll be able to measure oxygen.
I have a multiple question, but first of all, you showed this lambda profile, What is the absorption? I didn't understand that there's two peaks around plus and minus velocity. What is it? Can you explain?
Oh yeah.
Only one had absorption and
Let me show you a picture.
yes, here. It was here as well.
Let me take the figure one. Yes. So this is actually one line that goes like that. Okay. And you have interstellar medium absorption because this is H1. All the H1, all the neutral hydrogen you have between you and there is between you and the star is absorbing. And it's absorbing at a certain wavelength that's typically close to the center of the line. It's not too, depends on which velocity the interstellar medium is moving, but it's typically not super high speeds. So it's around close to zero, and that's why you see this. That's absorption from interstellar medium.
And why is one side more absorbed than the other? So you have one, the red ring, for example, is more absorbed because the product comes from one side on one transit, right? But it should be on the other side as well, no?
This is a giant hydrogen cloud around the planet. Okay, so it's moving together with the planet, but is leaving the planet. So what's happening to this cloud of hydrogen? It's being pushed away by the solar wind.
Okay. Yes.
Okay,
Yeah.
so it's coming towards you because you're looking in transit. It's coming towards you, so you see it blue shifted, right? So you have blue shifted absorption because that hydrogen is coming towards you, right? And that's why you see the absorption here towards the blue, and you see little absorption towards the red.
It's P Cygni profiles, no?
It's a sort of P Cygni profile. Yes, it's the same,
That's
it's the
in
same
between.
concept. It's exactly the same concept.
You said POLLUX would make multiple things simultaneously, but the far UV was left out.
Yes.
Is there a reason for this?
Yes.
You mean extreme UV? FUV is
100 to 120 nanometer is not simultaneously. Or because there is no material which can filter it out.
Correct. Yes. You see this? This part is the one that we call FUV, okay, or the FUV arm. It's the Moxter stream blue part of the far UV, and we can't split the light between here and here with dichroic that works. Simply, there is no material that there is no dichroic material that can do that in a good enough way for enabling all of that simultaneously.
And final question, you said the serviceable module is putting some constraint in terms of engineering. So POLLUX is like all with respect to the entrance, so it's a pinhole or a slit. But when you place the instrument inside the bay, I mean, it might not be maybe off by whatever millimeters. How do we align this potentially? Yeah, there is no concept, no idea, no one knows.
Oh yeah, thank you very much, Luca, for this nice presentation. Actually, I have the same question with the far UV. Maybe let's jump to the science topic again. You mentioned this alphanic radius, which might be a possible explanation why the planet appears dark sometimes. Maybe a very naive question. So what about moons, possible moons surrounding the planet as well?
They're not, these planets are too close to the star. Moons won't be stable. Okay.
I have a question concerning the ocean glint, or first, the other three instruments, they have no polarimetric properties, or do they?
Yes. So the coronagraph has to be able to not only take pictures like this one, okay, but put something where the planets are and take a spectrum of these planets. The spectrum is going to be very low resolution. You see the resolution of the spectra, and these spectra should also be in polarimetric mode. So you should be able to get Stokes Q and U of these planets as well.
So then I think you didn't tell us what is the power of polarimetry because there you have the combination of high spectral resolution and polarimetry, which is enormous, I think. But what is the science case? What do you think is really important for the polarimetry? If you can do this kind of low resolution polarimetric features already with the coronagraph, like the ocean glint, what about high resolution polarimetry?
So there is practically, so the exoplanet science case does not really have strong requirements on the polarimeter. We could do almost our entire science case without the polarimeter. Okay? There are two things for which it can be useful. The first one is the star-planet interaction science case, for which we require to get the magnetic field of the star, to monitor the magnetic field of the star. That's the first one. And the second one, we can do the cross-correlation thing. The cross-correlation technique can be done in polarimetry as well. Okay. We can extract much smaller signal from the cross-correlation at high resolution compared to the low resolution, thanks to the cross-correlation. Okay, so you can go a lot deeper thanks to the high resolution spectropolarimeter. A lot deeper than this.
For example, when you think about, say, the question in the UV, do you have more like a molecular scattering continuum or particles? They should be very different in polarimetry, actually, because
should be different. Yes.
So maybe one can also think about where maybe there is actually more science that we can do with the polarimetry. I think Christiane had some connections with people who can do this polarimetry relief transfer for molecules, and then you can actually see something.
We haven't. So the problem is that if we have the star if we get the light from the star and the planet, both of them, the stellar light is overwhelming. Okay, we will never be able. We've spent actually all the first part of POLLUX development in the last years trying to figure out whether we can do anything with the polarimeter, having both star and planet, and it's impossible. Okay, even with the 15-meter space telescope, we could not do it. We need at least twice as much. It was impossible. We need to be able to separate star and planet, and that's where the cross correlations comes in. The continuum will be a problem because it will be hard to remove the stellar contamination on the polarimetric measurement.
So that's why in the coronagraph that's possible then, and there you get a better signal on the.
The coronagraph you can do that because you don't have the star.
Right. Thanks.
Okay. Another kind of question here.
Yes, very cool. I mean, I understand you can do you look at the sun, do the same thing, and go to the other side and go to the same thing, so to speak, right? It's really cool. My question is just, okay, in the Earth sun case, we know roughly what the solar field and there's a flare, and Earth we have also magnetic field, you know what's there, but if you look the other side, you look at the sun or whatever star, and you know, like you see the flares, or you think that there's flares, and you see me or something, and you see in the planet. What do you know? Can you see the aurora? Are you talking, or you see some? What do we see in the exoplanet side?
So auroras, we tried with Hubble to look at auroras, and it didn't work.
Yeah.
And we don't know why. It can be that simply we do not have enough collecting area, or the planet simply did not have an aurora. We don't know.
But I thought the other side is how it's like Jupiter. You saw like kind of star-ish thing having aurora-ish thing because you have some connection. I don't know whether
This was observation in the millimeter. So we did this with ALMA.
okay. Here you
For brown dwarfs, it was kind of there, but equally hard to find.
It's really hard.
So what would you see then the planet side? Do you see some expanded atmosphere?
You see on a planet what one would expect to see is let me Here, you see Lyman alpha,
Okay.
and you see absorption during transit.
Yeah.
And when you look instead at quadrature, you don't see absorption, but you see an extra emission. That's what you expect to see. Or close to quadrature.
Right. And then second, this is not a science question, but you said it's a kind of slot you are trying to candidate, but basically, I think this is a European contribution, so they will never say no, right? So that means talking like the scale of the instrument might change or something, right?
So they will say no only in the moment in which the instrument exceeds mass and volume.
Oh, yeah, yes. So as long as you fulfill the technical.
If you fulfill mass and volume, they will never say no.
Yes, I thought it's basically, yeah.
So on the NASA side, we're pretty safe. The other instruments that they could go in there, they thought about a UV coronagraph. It's super tough to build now an optical coronagraph. Making a UV coronagraph, it's a dream. Okay, particularly if they want to be at TRL5 in 29, there is no way. It's literally impossible.
I have a technical question. The cross-correlation method is used for pattern recognition in a noisy environment.
Mhm.
Have you tested it, or do we have any ideas what kind of background noise level would be too much not to recognize the patterns?
We are currently doing this kind of technique with data that have a quality that is significantly lower compared to what we're gonna get from this. Okay, so we are gonna certainly be able to do it. Question is to which kind of planet we can apply it. Whether we can do it on something as small as Earth or Neptune at far from the star, we don't know. This is something that we will have to figure out. We don't know that yet. We know that we can do that. For the planets that we currently observe, we might even be able to, not even need to see the single lights sticking out of the noise. This for the planets that we do now. So we hope to be able to do it, to go a lot deeper with cross correlation.
Okay, so that was very nice final sentence for. Thank you again for.